What's going down, Team Geometry? This is our lesson 6.8, quadrilaterals in the Cartesian plane. Cartesian plane is the XY plane, another name for it. Take a moment, read the aim, and let's get into it. So, as you may have noticed from today's aim, we're going to be talking about quadrilaterals. Remind yourself of what they are. Hopefully you said four-sided polygons. We're going to be focusing not on the not parallelograms, but on parallelograms. They're a little bit more interesting. So quadrilaterals split off into two different types. One type is parallelograms. The main point about parallelograms is that their opposite sides are parallel. A property is also that their opposite sides are congruent, but the definition actually is just opposite sides parallel. And there's some other things too that you might know, like opposite angles are congruent, adjacent angles are supplementary, etc., etc. Alright, within parallelograms we have just general parallelograms, things that don't look that special but do satisfy the properties of a parallelogram. Let me just draw one for you here. Let me draw one for you here. Alright, so it turns out this thing draws better with black ink instead of white ink. Alright. So this is a general parallelogram that I've shown right here. Just notice this side is parallel to this side parallel to the opposite side. So that would be a general parallelogram, not special. Not a rhombus, because a rhombus is a parallelogram in which all pairs of sides are congruent. It's an equilateral parallelogram. So this side would be congruent to that side, would be congruent to that side and that side. This actually looks like it could be a rhombus. But I don't know, measure it and I'm sure you'll find out that one of the sides isn't the same as the other. Rectangles are special parallelograms in which all angles are equal, so all the angles should be 90 degrees. Squares are sort of the offspring of rhombuses and rectangles. In a square, you have the properties of a rhombus. All the sides are equal, they're congruent. And you have the properties of a rectangle, all the angles are 90 degrees, or congruent. So squares are both rhombuses and rectangles, hence this offspring chart thing here. Alright, so those are the properties that you need to know about parallelograms, rhombuses, rectangles, and squares. So now let's try to apply some of those properties. So here's the first example. We are trying to form a parallelogram. We have a couple different options on how to do that. What I want you to picture is what the parallelogram should look like. There are a couple options you have already as you do this. I'm just going to show you one. You might think that CD would be a side and DE would be a side of the or another side of the parallelogram. So in that case, you're picturing the point F being somewhere in this region, like around here, so that you have the continuation of a parallelogram, something like that. Alright, so we're going to work with that option first. Well, what's the key point about a parallelogram? It's that opposite sides are parallel. So, let's look at the slope for CD first. If I want the slope for CD, that's a segment here, what I notice is that I have a rise of 1, 2, 3, 4, 5, and a run of 1. This is positive slope because it leans to the right. So the slope of this line is 5 over 1. Alright, the opposite side should be parallel to it, so it should also have a slope of 5 over 1. So allow me to go 5 up, 1 to the right from point E to make sure my opposite sides are parallel. Well, if I do that, up 5, I've got 1, 2, 3, 4, 5, 1 to the right. PAL would put me at the point 5, 3. That's where I think I could put F, so that I have formed a delightful parallelogram. This looks like a 3-year-old drawing. Alright, so I could form a parallelogram. And in case you're wondering, as you may recall, the symbol for parallel, we do a little arrow. I am arguing that those two sides are parallel. Hopefully you believe me also that these sides here are parallel, these sides right there and right there. Take a moment, just confirm that it's true. Alright, next example. So, you may have actually thought of the parallelogram as looking a little bit different. or differently. So maybe you had thought that CE was a side and DE was a side of the parallelogram. And that's fine. That means your F would be somewhere over here so that your parallelogram would look something like what I'm tracing right now. That's what you had envisioned. So let's figure out where F should go if that were your answer. So yes, there are multiple answers to this. They're all right. Don't worry about it. So I'm going to first find the slope of CE because I want, in my parallelogram, opposite sides to be parallel. So as you can see, I found my slope for CE to end up being negative, leans to the left, and the rise was 4, the run was 5. I got negative 4/5 for my slope for this line segment CE, which is one of the sides of the parallelogram. Well, the opposite side should be parallel to it. That's what parallelogram means. So I want something to go from D to some point F that also has a slope of negative 4/5. Take a moment and see if you can figure out where that should go. So I think it should go right there. Did I count my boxes right? 1, 2, 3, 4, 5. I think so. Alright, so this looks like it is the point F now at negative, I said negative, at the point negative 7, 1. Let me just show what my whole parallelogram would look like. There it is, purple and lovely. And just notice as a check, the slope from E to D, take a moment to figure out what's the slope from E to D. Hopefully you said negative 1/6. Sorry, it's a positive slope. Hopefully you said positive 1/6, as in 1 down, so negative 1, negative 6 to the right. So positive 1/6 was your slope. And just notice that that's what happens here for CF. Go 1 down, and then 6 to the left. So you have a slope of positive 1/6 here, positive 1/6 here. These opposite sides are parallel. These opposite sides are parallel. You have a great parallelogram. Follow-up question, is it a rectangle? Well, we just sort of alluded to that. Pause, think about what your answer would be. I would say, well, the slope of DE is 1/6, and if I compare my two sides, one having a slope of 1/6 and the other a slope of negative 4/5, my conclusion would be, and pow, can you see it? I think you can see it. This right here would be my I'll put it over here. This would be my response to the question. Alright, we're well on our way. We're at slide 5 of 9, in case you're like, when will this be over? L1 negative attitude. Alright, example 3, take a moment, pause, read it. If only I had a picture, you're saying to yourself. Well, pow, I have a picture myself. Perfectly drawn. Try to draw one for yourself. No chance it'll be this good, but you do what you can. Alright, so take a moment to figure out what do we know that's important. Well, one thing is that this is a square, so keep in mind I want all my sides to be congruent. I want all my angles to be 90 degrees. They tell me that one of the vertices is at 1, A. I don't really know where to put that. I know 1 is the x value, so it's somewhere here on the vertical line. But I don't know, is it here, is it there? First quadrant, fourth quadrant. That's not helpful. I'm going to go to this point that I do know. Alright, so I know 4, 4 looks like it should be right around there. And 6, 1. 6, 1. We'll say is right there. Okay, so possible location of the fourth vertex. So let me say, it could be something like this for my, those could form a side. Like maybe they form a diagonal, but I'm going to say for now that these form a side. So then the square maybe looks like this. That's square-ish. So now let's try to get a little bit clever here. I know that in a square, ultimately if I knew what my square looked like, let me just draw a little mock. If I had my square, let's pretend it looks like this over here. Alright, so this square, this square, can I move just this square? And I can't. Okay, here we go. So I'm saying that like the square might look like this. I mean, this could be the square. So if that's the square, Well, I do know some things. I know each of the vertex angles should be 90 degrees. And I know all of the sides should actually be the exact same length. So I can use that in sort of a creative way. If I find the slope of the line, that's what I've set out here. If I find the slope of that side, which again is probably this side here, if I find the slope, I believe from 1 to 4 is 3, and from 6 to 4 is 2. Well, I know the slope of this line segment, this side, is now, it's negative because it leans to the left, negative 3 over 2. So that's negative 3 over 2. And if you're hating, if you're like, what would be negative, I don't know, it depends on your perspective. I could say that 2 is negative because I went up 3 and 2 to the left. Maybe you were thinking I went plus 2, negative 3. It doesn't really matter to me. But as long as you know this is negative, you're good to go. All right, anyway, so this line has a slope of negative 3 over 2. Well, I know the side next to it, the two sides next to it, should be perpendicular. I meant for that to be a laser pointer. The two sides here and here should be perpendicular to that. So if the slope of one of this side in blue is negative 3 over 2, I think the perpendicular slope would be positive 2/3. So I can use that to say, well, for example, from this point to wherever my vertex should end up, the slope of this should be 2 over 3. So if I go up 2, I should go to the right 3, or if I go down 2, I go left 3. So down 2, left 3. If you're like, what? L1, call out. Negative 2, negative 3, just recall, a negative divided by a negative is still a positive. So these are the same thing. So I can drop 2 and go 3 to the left to find my new vertex. Think about where that would be. If you said 1, 2, then you're a super genius. So in like fashion, if we know the slope of this line is negative 2 over 3, as in you dropped 2 and you went 3 to the left, to get my other vertex here, I should also be able to drop 2 and go 3 to the left. I think dropping 2 would put me at negative 1. And then I think going 3 to the left from 6 would put me at 3. So I'm here at like 3, negative 1. Yeah, that looks great. Anyway, as I was saying, so 3, 1 would be my next vertex. And so this last side here should look like this. Just take a moment to double check. The slope between 1, 2 and 3, negative 1. Hopefully, it's going to be negative 3 over 2, which I believe it is. And also, it is perpendicular to this green, to both green segments, meaning these angles here and here are 90 degrees. So I have 4 right angles. If you take a moment to do Pythag, you'll see you'll just keep getting 3 squared plus 2 squared equals c squared, and so you'll get root 13 for all of your sides. So all sides are equal, like we are supposed to have. All angles are 90. I'm confident that this is a solution, and I don't really appreciate them giving me A, but I'll just tell them for bonus money, by the way, you didn't ask, but A is 2. You're welcome. Alright, so I'm just going to go a little faster on this one. Pause, take a moment, process the question. Again, as soon as you tell me parallelogram, I tell you that. It says opposite sides are parallel if you can't read my handwriting. So I need the opposite sides to be parallel. So I need the slope of this line to be the same as the slope of this line. Well, I can calculate the slope of this. It looks sort of scary because there are letters there instead of numbers. Or I guess, I don't know. Didn't you learn how to read before you learned how to count? So maybe it's more familiar. But let's take a moment to figure out the rise over run for this segment right here. Now I'm doing it old school. Is that really a thing? I'm doing it y2 minus y1 over x2 minus x1. I get b minus 1 over a as my slope for this segment right here. You could have also just done, okay, this is at negative a, that means I have to move a units to get to the y-axis, and then if this is at b, and b would be this whole distance here, I just have to go b minus 1 for my rise. So you could have actually figured it out without this, I guess, but, well, I did it this way. So this is the slope I want for the opposite side. So I want the run to be a and the rise to be b minus 1. So we can get into this complicated thing here, and I can be like, okay, well, I have to drop b minus 1 every time I go a units to the left. So if I was at 6 and I subtract a, I go 6, I'm at 6 and I move a units this way, well then this point here would be 6 minus a for the x coordinate. It says a. Does that say it? It looks like a. And also, if I'm at b and I subtract b minus 1, well, let's get our algebra hats back on. We have an algebra hat. b minus 1. Okay, well, let's distribute b minus b plus 1. That's b minus b. Nothing. So 0 plus 1 is 1. Okay, so 1 is my y value. So now I'm like, okay, so that vertex that you were looking for, I'm just trying to get a parentheses, seriously. Okay, whatever. So that point that I'm looking for is 6 minus a comma 1. And so at this point you're probably like, that was super complicated, I have to pause and look through all this algebra. I'll just point out, if I were you, what I would have probably done, quite honestly. I would have looked at this side and been like, wait, this is pretty easy to figure out. That's just 6. And if I notice, it's just 6 horizontally. So that means the y value doesn't change. So if I'm at 0 and I move 0 comma b and I move 6 units to the right, well, now I'm at 6 comma b. And if it's a parallelogram, I know the opposite sides are parallel. I also know they're congruent. So I could actually tell you that the opposite side is also 6. So then I could say, well, if I'm going to move 6 units horizontally, the y value won't change, so I know it's 1. And now I just have to figure out what is negative a plus 6. And if you look at it, negative a plus 6 can also be written as 6 minus a. I can't combine them because they're not like terms. So from there I could have just said, well, I needed to add 6 to this, so it's negative a plus 6, or 6 minus a, however you want to write it. But without any of this crazy slope business and all this work, I could have also found this pretty quickly. Last example. Try not to cry. Take a moment, pause, read it. I bet you're wishing you had a picture. Blow! There we go. So let me try to move this so I can see it a little better. There we go. Alright, so I'm trying to find the intersection point of the diagonals, and I realize that that is a fancy sounding way to ask me a really simple question. Because, as I'm sure you remember from one of my thrilling lectures way back in the day about parallelograms, the diagonals, you want to say it, yep, they bisect each other. So what that means is they cut each other in half. So this half and this is half. This segment is equal to this segment. So in other words, the thing that's actually most impressive is that this point is the blank of this segment and the blank of this segment. What goes in the blank? That's right, you guessed it, the midpoint. So I don't have to do a whole bunch of fancy stuff. This question is really just asking me what's the midpoint of these segments. Well, I can find either the midpoint of this segment or the midpoint of this segment, because guess what? They're the same point. They meet right there. So I just get to choose, would I rather use the midpoint formula on A and T or on H and R? 0 is always nice to work on. So I'm going to find the midpoint of AT, and then I'll be done with this question. Let me see, can I shrink this and move it over here? Alright, so now I got some space to work. Midpoint formula, what is it? Hopefully you said something like that. So I'll plug in my points. So I think I have 6 plus nothing over 2. That's a 2. It's a 2. It's a 2. Alright, and then I have 6 plus negative 2 over 2. Just a thing I noticed too, a lot of times people forget parentheses, try not to be like them. Attention to detail. That's what separates us from the barbarians. That and hygiene. Krakow. Negative 3 comma 2. So what is negative? Why did I say that? 3 comma 2 is the midpoint, and that seems pretty good. This is like the most accurate drawing of all time, but I know this should be in the first quadrant. That's why whoever said negative 3 for the x-coordinate is a fool. So that seems good. What you can do right now, check to see if HR's midpoint is the same, because hopefully it is, if this is indeed a parallelogram. And I think it is, so we win. Alright, so just notice the common thread in all of these questions is actually just using basic properties of parallelograms, quadrilaterals, well, I guess really just parallelograms. So know what the different properties are, apply them, and good luck to you.